The Big Bang is the most misunderstood idea in all of science. Most people hear the name and picture an explosion. Something small, something hot, something that detonated inside empty space and sent matter flying outward in all directions. That's not what happened. There was no empty space to explode into. Space itself expanded. Everything that exists, every galaxy, every atom, every inch of distance between things, stretched outward from an unimaginably hot, dense state roughly 13.8 billion years ago. That's the actual idea. And most people never get told that part. Here's what most people miss about where this theory even came from. Einstein didn't propose it. He built the framework that made it inevitable and then spent years trying to avoid it. His general relativity equations, published in 1915, described gravity not as a force pulling things together, but as a curvature of space-time caused by mass and energy. When you run those equations at the scale of the whole universe, they don't give you a stable, static cosmos. They give you one that's either expanding or contracting. Einstein didn't like that. He added a term called the cosmological constant just to hold the universe still. It was the wrong call. A Belgian priest and physicist named Georges Lemaître looked at the same equations, took them seriously, and in 1927 proposed what he called the hypothesis of the primeval atom. The universe had a beginning. Everything started compressed into a single point and expanded outward from there. 2 years later, Edwin Hubble confirmed it observationally. Galaxies are moving away from us. The farther they are, the faster they're receding. Run that motion backward and everything converges. Einstein eventually visited Hubble, looked at the data, and called his cosmological constant the greatest blunder of his life. The theory rests on 3 pillars, and all 3 have held up. First, the expanding universe. Hubble's observation still stands. Every galaxy cluster is flying apart from every other. Space is growing. That's not disputed. Second, the abundance of light elements. In the first few minutes after the bang, the universe was a nuclear furnace. Protons and neutrons were smashing together fast enough to fuse. The theory predicts specific ratios of hydrogen, helium, and lithium that should have come out of that period. We measure those ratios in the oldest, most primitive parts of the universe. They match. Third, the cosmic microwave background. This one closed the argument. About 380,000 years after the bang, the universe had cooled enough for electrons to bind to protons and form neutral hydrogen atoms. Before that point, the universe was opaque. Light couldn't travel freely. The moment those atoms formed, light broke loose and flooded through space in every direction. That ancient light is still out there. It's everywhere. Stretched by billions of years of expansion into microwave frequencies, it fills the entire sky at a nearly uniform temperature of about 2.7 Kelvin. In 1964, Arno Penzias and Robert Wilson picked it up accidentally with a radio antenna in New Jersey. They thought it was pigeon droppings fouling their equipment. It was the oldest light in the universe. The CMB confirmed that the universe had a hot, dense past. It confirmed that the bang happened. The steady-state theorists who argued the universe had no beginning and was always more or less as it is now couldn't explain it. The CMB put them out of business. Now here's the honest part. The theory doesn't actually describe the singularity itself. At the very first moment, the density and temperature are infinite in the equations. General relativity breaks down. The physics we have cannot describe what was happening at time zero. And what came before? That question might not even be meaningful. Time, as we understand it, appears to have begun with the expansion of space. Asking what existed before the Big Bang may be like asking what's south of the South Pole. The theory also says nothing useful about a cause. It describes what happened after the universe began expanding. It does not explain why it began. None of that makes the model weak. The Big Bang is not a guess. It's not a religion. It's not a headline somebody made up. It is the most precisely tested, most thoroughly confirmed framework in the history of cosmology. The expanding universe, the light element abundances, the cosmic microwave background, the large-scale structure of galaxy clusters, all of it fits. Every test we've thrown at it for 60 years has come back saying the same thing. The Big Bang theory has a problem, actually a few of them. Not small problems either. The kind that, if you sit with them long enough, make the whole picture feel incomplete. 2 in particular have bothered cosmologists for decades. The horizon problem and the flatness problem. Neither one gets talked about enough. Here's the horizon problem. Look at opposite ends of the observable universe. We're talking about regions so far apart that light from one side has never had time to reach the other. Not in 13.8 billion years. They've never been in contact, and yet when you measure the temperature of the cosmic microwave background in both directions, they match, almost exactly, to 1 part in 100,000. That shouldn't be possible. Things reach the same temperature by exchanging energy. You put two objects in contact long enough and they equalize, but these two regions were never in contact. So why do they match? The standard Big Bang model has no answer. It just says that's what you get, which isn't an answer. Then there's the flatness problem. The universe is geometrically flat. Not kind of flat. Remarkably, almost suspiciously flat. In general relativity, the geometry of the universe depends on its density. Too much mass and it curves closed like a sphere. Too little and it curves open like a saddle. Exactly the right density and it's flat. The universe sits right at that critical density. The thing is, flatness is unstable. Any tiny deviation in the early universe would have grown over time into something dramatic. For the universe to be this flat today, the initial conditions at the Big Bang would have had to be tuned to extraordinary precision. We're talking fine-tuning at better than 1 part in 10 to the 60th. The standard Big Bang model doesn't explain that either. It just says it started that way. Alan Guth was a young physicist in 1980 when he proposed the fix: inflation. The idea is that a fraction of a second after the Big Bang, something caused the universe to expand exponentially fast. Not the ordinary expansion we see today, something far more violent. The universe doubled in size, then doubled again, roughly 60 to 100 times in an interval so small it makes a nanosecond look like an eternity. We're talking something like 10 to the minus 32 seconds. The universe went from subatomic to roughly the size of a grapefruit before normal expansion took over. That's not a typo. What drove it? A hypothetical field called the inflaton. Think of it the way you'd think of a ball sitting high on a slope. It has potential energy. It hasn't rolled down yet. The inflaton field was stuck in a high-energy state, and that stored energy drove the expansion. When the field finally rolled down to its minimum, inflation ended. The energy dumped into the universe as a violent burst of heat and particle creation. That's what we call reheating, and that's essentially where the hot dense state of the traditional Big Bang picks up. Now here's what most people miss. Inflation solves both problems in one shot. The horizon problem disappears because regions that look causally disconnected today were actually in contact before inflation stretched them apart. They had time to equalize. Then inflation yanked them so far apart they look like they've never met. The flatness problem disappears because any curvature gets stretched away. Inflate a crumpled piece of paper enough and it looks flat. Same idea. Whatever the initial geometry was, inflation irons it out. But that's not even the most interesting part. Before inflation ended, the universe was operating at quantum scales. And at quantum scales, nothing is perfectly smooth. Quantum fluctuations, tiny random ripples in the inflaton field were getting stretched from subatomic to cosmic. Those fluctuations became variations in density across the early universe. Regions slightly denser than average eventually collapsed under gravity into galaxies and galaxy clusters. The large-scale structure of everything you can see traces back to quantum noise amplified by inflation. The CMB's temperature fluctuations, those tiny ripples that the Planck satellite mapped in extraordinary detail, are the frozen imprint of those original quantum jiggles. The spectrum of those fluctuations was predicted to be nearly scale invariant, meaning roughly the same amplitude across a wide range of scales. Observations confirmed it. That match between prediction and observation is the best evidence we have that inflation actually happened. What we don't know is which version of inflation happened. Dozens of inflationary models exist. Chaotic inflation, natural inflation, Starobinsky inflation, new inflation. Each one uses a different shape for the inflaton's potential energy curve. Each one makes slightly different predictions, and current observations can't cleanly separate them. We know something like inflation almost certainly occurred. The evidence is strong. But the specific model, the precise field, the exact mechanism, nobody can tell you that yet. Inflation solves the problems beautifully, but the specific mechanism that drove it remains completely unknown. About 27% of the universe is made of something we cannot see, cannot detect, and have no confirmed idea what it actually is. That's not a gap in the data. That's not a rounding error. That's the current state of modern physics, and it's been that way for decades. Most people hear dark matter and assume it's a fringe idea. It's not. It's one of the most well-supported inferences in all of cosmology. We just have no idea what the thing actually is. Here's where it starts, the 1970s. Vera Rubin is measuring how fast stars orbit inside galaxies. The expectation is straightforward. Stars near the galactic center, where most of the visible mass is, should orbit fast. Stars on the outer edges should orbit slower. Same reason the outer planets in our solar system move slower than the inner ones. Gravity drops off with distance. That's the physics. What Rubin found was completely different. The outer stars weren't slowing down. They were moving at roughly the same speed as the inner ones, sometimes faster. The rotation curves were flat when they should have been falling. You run the math on that and something doesn't work. Either the gravity out there is stronger than the visible matter can explain, or gravity itself doesn't work the way we think at galactic scales. Most physicists took option 1. There's more mass out there. We just can't see it. That's the rotation curve problem, and it's not unique to one galaxy. Rubin measured dozens. Same result every time. Flat curves, excess gravity, invisible mass. That pattern holds across galaxy types, across distances, across the entire observable universe. It's not a fluke. Something real is causing it. Gravitational lensing backs this up. When light from a distant object passes near a massive structure, gravity bends the path of that light. We can measure the bending. We can calculate how much mass caused it. When you look at galaxy clusters and run those numbers, the lensing effect is far stronger than the visible matter alone can produce. The cluster is bending light like it's carrying several times more mass than we can actually see. That extra mass has to be somewhere. It's just not glowing. Then there's the bullet cluster. 2 galaxy clusters that collided and passed through each other. When they hit, the hot gas, the visible matter, got slowed down by electromagnetic drag and lagged behind. But the gravitational mass, mapped through lensing, kept moving. It separated from the gas. You can see it in the maps. The invisible stuff didn't interact, it just kept going straight through like nothing happened. That's huge. That's not a model prediction or a theoretical inference. That's a direct observation of invisible mass behaving exactly the way dark matter should behave, separate from normal matter, unaffected by electromagnetic forces, just gravity. Large-scale structure simulations make the same point. If you try to model how the universe formed its web of filaments and galaxy clusters using only visible matter, the simulations don't match reality. Structure forms too slowly, in the wrong places, at the wrong scales. Add dark matter into the model and it works. The simulations line up with what we actually observe. Dark matter isn't just a fix for rotation curves. It's apparently a load-bearing part of how the entire universe is structured. So what is it? Here's what most people miss. We've actually ruled out a lot of things. It's not regular matter we've just missed, like cold gas clouds or faint stars. We can account for those. It's not black holes filling the gaps, at least not conventional stellar mass black holes. Gravitational microlensing surveys looked for exactly that, and came back with nothing close to the required amount. It's not antimatter. Antimatter and matter annihilate on contact and we'd see the gamma ray signal. That signal isn't there. The leading candidates are WIMPs and axions. WIMPs, weakly interacting massive particles, are hypothetical particles that interact through gravity and the weak nuclear force and nothing else. They're invisible, they're massive, and they'd naturally produce the right abundance from the early universe if the physics works out. Axions are much lighter, originally proposed to solve a completely separate problem in particle physics, but they'd also behave like dark matter if they exist. Both candidates are theoretically clean. Both have motivated decades of experiments. The experiments have found nothing. Underground detectors shielded from cosmic rays, cooled to near absolute zero, sensitive enough to register individual particle interactions. Nothing. Direct detection has come up empty run after run. Particle colliders have searched for WIMP signatures. Nothing. Axion searches are ongoing, getting more sensitive, still empty. We've built better and better instruments specifically to catch this thing, and it keeps not showing up. That's the uncomfortable position physics is in right now. The evidence that dark matter exists is extremely strong. The rotation curves, the lensing, the bullet cluster, the simulations, all of it points to the same conclusion. There's mass out there that isn't made of anything in the standard model, but every attempt to catch it in a detector has failed. We're confident it's real. We can't tell you what it's made of. The detectors get more sensitive every year, and every year they come back empty. In 1998, two separate teams of astronomers went looking for proof that the universe was slowing down. That was the assumption. Expansion started with the Big Bang. Gravity pulls everything back together, so the expansion rate should be dropping. Both teams were measuring distant Type 1a supernovae. These are reliable, same brightness every time, so you can use them like cosmic rulers. You measure how bright they appear, you calculate how far away they are, you figure out how fast space was expanding when that light left. Both teams did the math. Both teams got the same answer. The universe isn't slowing down at all, it's speeding up. Nobody expected that. That result won the Nobel Prize in 2011, and it completely broke the standard model of cosmology as it existed. Something is pushing space apart, and it's getting stronger over time. That something got named dark energy. Great name. Tells you almost nothing. Here's what most people miss about dark energy. It's not a force in the way gravity is a force. It's not radiation. It's not a particle anyone has detected. The leading explanation is that it's energy inherent to empty space itself. Not empty space with stuff removed. Actual vacuum. The quantum vacuum has energy, and that energy has a repulsive effect at cosmological scales. Einstein actually built something like this into his equations first. In 1917, he added a term called the cosmological constant, a kind of built-in repulsion to keep his model of the universe from collapsing under its own gravity. Then Hubble showed the universe was expanding and Einstein dropped it. Called it his greatest blunder. He was wrong about dropping it. The constant he invented for the wrong reason turns out to describe the accelerating expansion perfectly. That's either poetic or deeply frustrating, depending on your tolerance for that kind of thing. Dark energy makes up roughly 68% of the total energy content of the universe. Dark matter accounts for about 27%. Everything you've ever seen, touched, or measured, every star, every planet, every atom of normal matter, adds up to around 5%. You're living in a universe that is almost entirely made of things we can't directly observe. Dark energy is the bigger piece. It's not clustered around galaxies the way dark matter is. It's spread uniformly through all of space. It doesn't dilute as the universe expands. More space means more dark energy, which means more expansion, which means more space. It compounds. That's why the acceleration is getting worse over time, not better. The cosmological constant model is the simplest explanation. Vacuum energy is real. It has a fixed value, and that value is what it is. This is called lambda CDM, and it's the standard model of modern cosmology. It fits the data. The problem is that when you try to calculate what the vacuum energy should be, from first principles using quantum field theory, the number you get is off from the observed value by about 120 orders of magnitude. That's not a rounding error. That's the worst prediction in the history of physics. The theory says it should be enormous. The universe says it's tiny. Nobody knows why. So there are other models. Quintessence treats dark energy as a dynamic field rather than a fixed constant. The field has a value that changes over time, like the inflaton field from cosmic inflation. Maybe dark energy was stronger in the early universe. Maybe it weakens. It rolls down a potential like a ball rolling down a hill. This would explain the cosmological constant problem by saying there is no constant, just a field that happens to have the value it has right now. The model is flexible. That's also its weakness. It's hard to distinguish from a cosmological constant without extremely precise data. Then there's phantom energy. Phantom energy is what you get if dark energy isn't just constant or slowly varying, but actually grows without limit. If phantom energy is real, the expansion doesn't just keep accelerating, it eventually tears apart everything. Galaxy clusters first, then individual galaxies, then solar systems, then planets, then you. That's called the Big Rip. Most physicists consider it unlikely, not impossible. The 2024 DESI results changed the conversation. The Dark Energy Spectroscopic Instrument mapped millions of galaxies to trace how expansion has changed over time. What they found suggests dark energy may not be constant. The data fits better with a model where dark energy was stronger in the past and has been weakening. If that holds up, lambda CDM is wrong. Not slightly wrong, fundamentally wrong. The cosmological constant would have to go. It's early data, needs confirmation. But the fact that it's even a serious conversation shows how fragile the standard model actually is underneath all its success. One good dataset and the whole framework needs revision. What most people miss is that we named it before we understood it. Dark energy isn't a solution, It's a label for something we measured and couldn't explain. You can measure its effects precisely. The expansion rate, the geometry of the universe, the growth of large-scale structure, all of it is consistent with dark energy behaving a certain way. But the underlying mechanism is completely unknown. No particle, no field, no confirmed theoretical framework tells you what it fundamentally is. Dark energy makes up most of the universe, and we can't tell you what it is. Einstein's general relativity predicts objects so extreme that Einstein himself refused to believe they could actually form. He thought nature would find a way around it. Some loophole, some physical process that kicks in before things get that bad. He was wrong. Black holes are real, they're everywhere, and the universe makes them constantly. Here's the basic picture. A black hole is a region of space-time where gravity is so overwhelming that nothing escapes. Not gas, not particles, not light. The escape velocity exceeds the speed of light, and since nothing travels faster than light, nothing gets out. What most people miss is that a black hole isn't a thing sitting in space. It's a region, a geometry. Space itself curves so severely that all paths lead inward. The edge of that region is the event horizon, and this is where most people get it wrong. The event horizon is not a wall. It's not a surface you'd feel yourself crossing. It's a mathematical boundary, the point past which your future only points one direction. Inward. You cross it, and you don't feel anything unusual. You just can't come back. Ever. Inside the event horizon, the roles of space and time actually switch. Moving toward the singularity becomes as inevitable as moving forward in time. You can't stop it any more than you can stop time from passing. At the center is the singularity, infinite density, zero volume, and every equation we have for describing physics breaks down completely. General relativity hits a wall there. It stops giving useful answers. That's not a minor problem. That's the theory telling you it needs help from a better theory, one that combines gravity with quantum mechanics. We don't have that theory yet. The singularity is basically where our understanding ends. Black holes come in different sizes. Stellar mass black holes form when a massive star runs out of fuel. The outward pressure that held the star up disappears. Gravity wins instantly. The core collapses, the outer layers explode as a supernova, and what's left behind is a black hole anywhere from a few times the mass of the Sun up to around 100 solar masses. These are scattered through every galaxy in enormous numbers. Our own galaxy probably has tens of millions of them. Then there are supermassive black holes, millions to billions of solar masses, sitting at the centers of almost every large galaxy. Nobody fully understands how they got that big. At the center of the Milky Way sits Sagittarius A star, about 4 million times the mass of the Sun. Stars near the galactic center orbit it at extraordinary speeds. We've tracked those orbits for decades now. The numbers only make sense if something 4 million solar masses is packed into a region smaller than our solar system. There's also a third category, primordial black holes. These are theoretical, potentially formed in the early universe, when density fluctuations were extreme enough to collapse regions of space directly, before any stars existed. Some physicists have proposed they could account for a portion of dark matter. No confirmed detection yet. Still on the table. Now here's where it gets strange. Hawking radiation. Stephen Hawking worked this out in 1974 and it shook the field. Quantum mechanics says that empty space isn't actually empty. Virtual particle pairs constantly pop in and out of existence near the event horizon. Normally they annihilate immediately, but right at the event horizon, one particle can fall in while the other escapes. The black hole has to pay for that. It loses energy. It slowly radiates. It evaporates. For a stellar mass black hole, the timescale is absurd. Far longer than the current age of the universe, many times over. But it happens. Black holes aren't permanent. They eventually disappear. That creates one of the deepest unsolved problems in all of physics, the information paradox. Everything that falls into a black hole carries information, the precise quantum state of every particle. When the black hole evaporates, Hawking radiation appears to be completely random, carrying no record of what fell in. That means the information is gone, and that violates one of the foundational rules of quantum mechanics, which says information is always preserved. You can scramble it, you can hide it, but you cannot destroy it. So either Hawking's calculation is missing something, or quantum mechanics needs revision, or the information escapes in some subtle way we haven't figured out yet. Physicists have been arguing about this for 50 years. No consensus. Hawking himself changed his position on it more than once. Here's what most people miss. The information paradox isn't just a technical puzzle. It's a signal that our two best theories of physics are fundamentally incompatible in the most extreme conditions. Quantum mechanics and general relativity each work brilliantly in their own domains. Throw them both at a black hole and they contradict each other. That's the problem nobody has solved. Then came 2019. The Event Horizon Telescope, a network of radio dishes spread across the entire planet, linked together to function as a single Earth-sized instrument. They targeted M87 star, a supermassive black hole 6.5 billion times the mass of the Sun, sitting 55 million light-years away. What came back was a glowing ring of superheated gas circling a dark central region. The shadow of the event horizon. The size matched what general relativity predicted. The shape matched. The physics matched. That image in 2019 wasn't just a photograph. It was confirmation that the most extreme objects the math allows are real. The standard model of particle physics treats every fundamental particle as a dimensionless point in space. No size, no structure, just a location where the math says something exists. That works surprisingly well. The standard model is one of the most successful theories ever written. But it has a problem, and the problem is gravity. Quantum mechanics and general relativity describe reality at two completely different scales, and when you try to combine them, the math breaks. You get infinities where you shouldn't. The equations stop making sense. For decades, physicists have been searching for something that bridges the gap. String theory is the most serious attempt anyone has made. Here's the core idea. Instead of a dimensionless point, every fundamental particle is actually a tiny one-dimensional string of energy. That's it. A vibrating loop or strand, too small to detect with anything we currently have. Different vibrational modes produce different particles. An electron is a string vibrating one way, a quark vibrates another. A photon is a different mode entirely. What looks like a zoo of separate particles is actually one object doing different things. That's the pitch, and on paper, it's genuinely elegant. The reason physicists took this seriously is that string theory naturally produces a graviton. A graviton is the hypothetical particle that carries gravitational force, the thing general relativity doesn't have a quantum version of. When you work through the string theory equations, the graviton falls out automatically. You don't have to add it by hand, it's just there. That's not a small thing. Every other attempt to quantize gravity produces nonsense. String theory at least produces something that looks like the right answer. That's why the smartest people in theoretical physics spent careers on it. What most people miss is the dimensions requirement. String theory doesn't work in 4 dimensions. The math only stays consistent in 10, 11 if you include M-theory, which we'll get to. So where are the extra 6 or 7 dimensions? Compactified. Curled up at scales so tiny that nothing we can build will ever detect them. The standard framing is that they're wrapped into geometric shapes called Calabi-Yau manifolds. Different shapes produce different physics, different particle masses, different force strengths, different constants. And here's where things get uncomfortable, the landscape problem. The string theory equations don't point to one unique solution. They allow roughly 10 to the power of 500 different vacuum states. That's not a typo, 10 to the 500th. Each one is a mathematically valid version of string theory. Each one corresponds to a universe with different physical constants, different laws. Some physicists look at that and see the multiverse handed to them on a plate. Of course, our universe is one of 10 to the 500th options. We happen to be in the one that allows atoms and stars and people. The rest exists somewhere we can't reach. Others look at the same number and see a catastrophe. A theory that predicts 10 to the 500 different universes predicts nothing. If your theory is consistent with every possible set of physics, it has no predictive power at all. That's not a theory. That's a framework for writing theories. M-theory is the attempt to hold everything together. By the mid-90s, physicists had built 5 separate versions of string theory, all of them mathematically consistent, all of them slightly different. Edward Witten showed in 1995 that all 5 are actually the same theory seen from different angles. The unified picture is M-theory, which operates in 11 dimensions and treats strings as special cases of higher dimensional objects called branes, membranes. 2-dimensional surfaces, 3-dimensional volumes, higher dimensional shapes that strings can end on. Branes became important fast. Some versions of cosmology are built around them. The The Big Bang as a collision between two brains floating in a higher dimensional bulk. That idea shows up in the next section, so we won't chase it here. The point is, M-theory is the deepest version of the string framework anyone has written down, and it's still incomplete. Here's what most people miss about where string theory actually stands. It's been 50 years, not 5, 50. The theory was born in the late 1960s as an attempt to describe the strong nuclear force, abandoned when quantum chromodynamics did that job better, then repurposed as a theory of everything in the 1980s, when people noticed it contained gravity. Since then, an enormous amount of mathematical machinery has been built. The ADS/CFT correspondence, which shows up in the holographic principle section later, came out of string theory. Real mathematical tools with real applications came out of it. String theorists aren't doing nothing, but none of it is a confirmed experimental prediction about the physical world. No sparticle discovered at the LHC, no extra dimension showing up in any detector anywhere. No gravitational wave signature that only string theory predicts. The compactification scales are too small to probe. The extra dimensions, if they exist, are invisible by design. String theory can't currently tell you anything about the real world that you could go and check. Some physicists defend it anyway. The mathematical output is too rich, too internally consistent, too connected to everything else in physics to be a coincidence. Others have walked away entirely, calling it a decades-long detour from actual progress. Lee Smolin wrote a whole book about it. Peter Voigt wrote another. The string theorists responded. The debate is still running. 50 years of work, some of the most talented physicists alive, and not a single confirmed experimental prediction. The multiverse is not one idea. It's at least 4 completely different ideas that happen to share a name. That's the first thing most people miss. They hear multiverse and picture one thing: parallel Earths, alternate timelines, comic book stuff. But the actual theoretical frameworks are completely different from each other. Different origins, different mechanisms, different problems they're trying to solve. Some of them don't even overlap. Brian Greene laid out 9 distinct types. You only need 4 to understand what's really going on. Level 1, the quilted multiverse. This one doesn't require exotic physics. It just requires that space is infinite, which most cosmologists already accept. Here's the logic. If space goes on forever, and matter can only arrange itself in a finite number of configurations, then every possible arrangement repeats. Somewhere out there, billions of light years past your observable horizon, there's a region of space that looks exactly like this one. Same Milky Way, same solar system, same you, reading the same thing, in the same chair. The copy isn't supernatural, it's just statistics applied to infinite volume. Your observable universe is roughly 93 billion light-years across. That's your bubble. But the actual universe doesn't stop there. If it keeps going forever, copies are inevitable. Not possible, inevitable. The distance to your nearest copy is so large the number has more digits than atoms in your observable universe. But the copy exists. That's the quilted multiverse. No new physics required, just space that doesn't end. Level 2, the inflationary multiverse. You need to know about eternal inflation first. Inflation is the rapid expansion that happened a fraction of a second after the Big Bang. In most inflationary models, inflation doesn't stop all at once. It stops in patches. One region slows down and becomes a universe. The surrounding region keeps inflating. Then another patch slows down. Another universe. This keeps going. Inflation never fully stops. It just keeps generating new bubble universes forever. Each bubble cools into a different configuration, different physical constants, different laws. In some bubbles, electrons are heavier. In some, gravity is stronger. In some, atoms never form. Your universe is one bubble that happened to cool into the parameters that allow stars and chemistry in you to exist. Here's what most people miss. These bubbles don't touch. They can't communicate. The space between them is expanding faster than light can cross it. You will never detect another bubble, ever. That's what makes this uncomfortable as a scientific claim. Level 3, many worlds. This one comes from quantum mechanics, not cosmology. Hugh Everett proposed it in 1957. The standard story in quantum mechanics is that particles exist in a superposition of states until you measure them. Measurement collapses the wave function into one outcome. Everett said, what if it doesn't collapse? What if every possible outcome actually happens and the universe branches? You measure a particle spinning up and the universe splits. In one branch you got spin up, In the other, you got spin down. Both are real. Both keep going. Apply this to every quantum event, everywhere, at every moment. The branching is constant, continuous. The number of parallel branches is not just large, it's incomprehensible. Everett's version is mathematically clean. It removes the measurement problem entirely. No collapse needed. The math just evolves and branches. Most physicists today take many worlds seriously. It's not fringe. It's one of the leading interpretations of quantum mechanics. The problem is you can't get to the other branches. They're not somewhere else in space. They're orthogonal quantum states, inaccessible by definition. Level 4. The mathematical multiverse. Max Tegmark pushed this one. His argument is strange. Every mathematical structure that is internally consistent physically exists somewhere. Not metaphorically, literally. Our universe is one mathematical structure. A different set of equations describes a different universe, and that universe is just as real as ours. There's no privileged status to the laws of physics as we know them. They're just one consistent mathematical framework among infinitely many. This is the most radical version. It says physical existence and mathematical existence are the same thing. Most physicists find this either fascinating or completely untestable, depending on their patience for that kind of thing. Here's the core problem with all four of them. They're almost entirely untestable. A universe outside your causal horizon can't send you a signal. A branching quantum timeline can't be visited. A bubble universe with different constants has never and will never interact with yours. Some physicists say that disqualifies the multiverse as science entirely. If a theory can't produce a prediction you can check, it's philosophy, not physics. That's a serious objection, and a lot of serious people hold it. But here's what most people miss. The multiverse isn't just speculation for its own sake. It's trying to answer something. Your universe has a cosmological constant tuned to 1 part in 10 to the power of 120. The masses of fundamental particles are set at values that allow atoms to exist. Gravity is just weak enough. The strong force is just strong enough. Change any of these by a tiny amount and you get nothing. No stars, no chemistry, no anything. If there's only one universe, that's an almost impossible coincidence. You'd have to explain why the constants landed exactly here. But if there are vast numbers of universes with randomly distributed constants, you'd expect some of them to be livable, and observers, by definition, can only exist in the livable ones. The multiverse doesn't just multiply universes for fun. It gives fine-tuning somewhere to go. Without a multiverse, you're left explaining why the universe looks almost exactly fine-tuned to produce us, and that's not a comfortable place to stand. String theory gets all the press, but there's another approach to quantum gravity that starts from a completely different direction. String theory says the problem is the particles. Replace them with strings and everything works. Loop quantum gravity says the problem is space-time itself, not the stuff in it. The geometry underneath everything. That's what needs to change. And what most people miss is that both approaches are trying to solve the exact same crisis. Quantum mechanics and general relativity flatly refuse to work together, and until something fixes that, physics is broken at its foundation. Here's what LQG actually proposes. Space isn't smooth and continuous at the smaller scales. Zoom in far enough. We're talking the Planck length, around 10 to the negative 35 meters, and space stops being a smooth fabric. It becomes a network. Discrete chunks, nodes connected by links called spin networks. Space is quantized the same way energy is quantized in an atom. There's a minimum unit of area, a minimum unit of volume, and you cannot go smaller. The geometry of the universe is built from these chunks the way matter is built from atoms. That's the core idea, and it doesn't require extra dimensions. It doesn't require strings. It just requires taking quantum mechanics seriously and applying it directly to the structure of space-time. Loop quantum cosmology takes that framework and applies it to the entire universe at once, and this is where it gets genuinely interesting. In standard Big Bang cosmology, you run the clock backward, and the universe gets hotter, denser, smaller. Eventually you hit a singularity. Infinite density, zero volume, the equations blow up and stop telling you anything. That's the wall. LQC removes the wall. Because space is discrete, you can't compress it to zero. As the universe contracts, density climbs toward the Planck scale and then something happens. The quantum geometry generates a repulsive force, not a force like electromagnetism, a geometric repulsion built into the fabric of quantized space itself. The contraction stops, the universe bounces, it expands again. What we call the Big Bang wasn't the beginning, it was the bounce, the big bounce, our universe expanding out of the collapse of a previous one. That's what LQC predicts. And unlike some of the multiverse scenarios we covered, this isn't pure speculation. It falls directly out of the math when you apply loop quantum gravity to a cosmological model. Abhay Ashtekar and his collaborators work through the numbers. The singularity doesn't just get softened, it disappears entirely. The universe before the bounce was contracting. Our universe is the rebound. Here's the key difference from the cyclic models that come up later in this series. LQC doesn't require the large-scale universe to eventually stop expanding and crunch back down. The bounce happens at the quantum scale. Our current universe can keep expanding forever, and the bounce still happened. It happened at the beginning, driven by quantum effects at Planck densities, not by a large-scale turnaround of the expansion. That's a subtle distinction, and most people collapse it together with ekpyrotic models or oscillating universe models. They're not the same thing. Now here's what LQC actually predicts that we could test. The pre-bounce universe left fingerprints. If a universe existed before ours, it had structure, quantum fluctuations, gravitational waves, physical processes. Some of that information survives the bounce and gets imprinted on the cosmic microwave background. Not the standard temperature fluctuations from inflation. Different patterns, power suppression at large scales, specific modifications to the primordial spectrum. Future CMB experiments with enough sensitivity might detect those imprints. Might. That word is doing a lot of work there. The predictions exist. The instruments capable of confirming them are being built or planned. We're not there yet. The honest state of affairs is this. LQG is mathematically self-consistent. It handles the singularity problem elegantly. It's background independent, meaning it doesn't assume a fixed space-time geometry and then put physics on top of it. The geometry is dynamic all the way down. Those are serious advantages, but it's incomplete. The full theory of loop quantum gravity, connecting the cosmological predictions back to particle physics and recovering general relativity cleanly at large scales, is still being worked out. Decades in, that work isn't finished. And the confirmed experimental predictions, same as string theory, 0. That's the uncomfortable comparison. String theory has 10 dimensions and a landscape of 10 to the 500 vacuum states, and 50 years of brilliant people working on it. LQG has quantized geometry, and the big bounce, and a different set of brilliant people working on it. They disagree on almost everything about approach and methodology. They agree that quantum gravity is the most important unsolved problem in physics. They both think the other side is probably wrong. LQG and string theory are both after the same thing, and both of them are still waiting for the experiment that would prove either one right. What if the Big Bang wasn't the beginning of everything, just the beginning of this cycle? That's the real question cyclic cosmology is asking, not a fringe idea, a serious one. Several independent models now propose that our universe is one in a long sequence, not the first, not the last, just the current iteration, and the reason physicists keep returning to this framework is straightforward. If the universe has always been cycling, you don't have to explain what came before it. There was always something before it. The problem evaporates. That's a powerful thing for a theory to do. The ekpyrotic model gets specific about the mechanism. Paul Steinhardt and Neil Turok developed it in 2001. The setup: your universe is a three-dimensional brain, essentially a membrane floating inside a higher dimensional space called the bulk. There's another brain out there, parallel to yours, invisible to every instrument you have. The Big Bang in this picture was not an explosion from a singularity. It was a collision. Two brains drifted together across the bulk, made contact, and the energy from that impact flooded your three-dimensional space as extreme heat and matter. Everything you see when you look at the night sky is the cooling aftermath of that collision. Here's what most people miss about ekpyrotic. The cycle doesn't stop there. After the collision, your universe expands. Normal cosmological history plays out across hundreds of billions of years, but the brains don't stay apart. They drift back toward each other, pulled by a weak force across the bulk. Another collision, another Big Bang. The whole sequence runs again. No beginning required, no end required. Just a perpetual back and forth between two brains that will never stop finding each other. The model also produces a smooth, flat universe without needing a separate inflationary epoch. That matters because nobody knows what actually drove inflation. Ekpyrotic sidesteps that problem entirely. But there's a fundamental challenge that haunts ekpyrotic cosmology. Each time the brains collide, entropy increases. The universe after collision 2 is more disordered than the universe after collision 1. After 100 collisions, after 1,000, the system accumulates disorder. Eventually, the universe could become so thermally degraded that another collision would be indistinguishable from thermal noise. You need a mechanism to reset entropy between cycles, to wipe the slate clean and allow fresh iterations. Steinhardt's team proposed that ekpyrotic expansion naturally dilutes entropy across enormous volumes, pushing disorder density low enough that the next collision can represent a true fresh beginning. It's an elegant solution on paper. But verifying it requires understanding entropy's behavior at scales far beyond our direct observational reach. The physics community remains divided on whether ekpyrotic truly solves this fundamental problem or simply relocates it beyond our current ability to check. Then you have Roger Penrose. His approach is different, stranger, in a lot of ways, more elegant. Penrose calls it conformal cyclic cosmology, CCC. The argument starts in the very distant future. You fast forward past every star burning out, past every black hole evaporating through Hawking radiation, past every massive particle decaying into pure radiation. What you're left with is a universe made entirely of massless particles, photons, things that travel at the speed of light and nothing else. Massless particles don't experience time the way you do. They don't register distance. A universe made exclusively of massless stuff has no physical sense of scale. That's the key to CCC. If you can stretch or compress a massless universe and nothing physically changes, its geometry can be conformally rescaled. Penrose argues that the cold, empty, featureless endpoint of one aeon is geometrically identical to the hot, dense starting point of the next. Your universe doesn't need to collapse. It doesn't need a crunch. It becomes the Big Bang of the following aeon through a conformal transformation. No new singularity, no missing physics, just a boundary where one universe's final state maps directly onto another universe's initial conditions. The end of everything becomes the beginning of everything. CCC makes a concrete prediction. That's what keeps it in scientific territory rather than pure philosophy. When massive black holes collide in the previous axion, Penrose argues those events leave faint traces in the cosmic microwave background of your universe. Concentric rings, circles of slightly anomalous temperature variation, subtle but there if you look. Penrose and his colleagues examined CMB data and claimed to find them. The broader cosmology community pushed back hard. The signals sit at the edge of what your data can cleanly resolve. Statistical methodology was disputed. Independent teams looked at the same datasets and reached different conclusions. Most cosmologists consider the evidence inconclusive. The prediction is specific, the confirmation is not, and that's where things stand. What cyclic models do better than anything else is dissolve the origins question entirely. You ask what caused the Big Bang. A cyclic model tells you the previous universe caused it. You push harder and ask what caused that one. Another universe before it. The question has no terminal point because there's no starting line to find. Some physicists hate this. They want a true beginning, a ground floor, something that counts as first. Others think demanding a cause for the universe assumes it needs one, and maybe that assumption is the problem. Cyclic models don't answer where the universe came from. They just move the question further back, which some people find satisfying and others find infuriating. The universe had a beginning, which means it probably has an end, and physicists have come up with several different ways it might go. And every single one of those endings ties back to dark energy. That's the thing most people miss. You can't talk about how the universe dies without talking about what dark energy actually does over time. Is it constant? Is it growing? Is it fading? We don't know yet. But each answer produces a completely different ending. So here's what we've got. The most likely scenario, given what we currently measure, is the big freeze. Heat death. Dark energy stays constant, the universe keeps expanding, and everything just spreads out. Galaxies drift so far apart they can no longer see each other. Star formation slows down because the gas clouds that feed it get stretched too thin. The last stars burn out. Black holes evaporate through Hawking radiation over timescales so absurd they barely qualify as numbers. A stellar mass black hole takes something like 10 to the power of 67 years to evaporate. The current age of the universe is 10 to the 14. You're waiting a very long time. Eventually what's left is a cold, dark, nearly empty space. A thin soup of particles with no energy gradients. No temperature differences, no processes, nothing happens and nothing keeps not happening forever. That's the big freeze. It's not dramatic, it's just over. The big rip is more violent. Here's what most people miss about dark energy. We assume it's constant, but there's a version called phantom energy, where it actually grows stronger over time. If that's true, the expansion of the universe doesn't just continue, it accelerates without limit. And at some point that acceleration overwhelms every other force in the universe. Galaxy clusters rip apart first, then individual galaxies, then solar systems, then planets shred, then molecules, then atoms themselves get torn apart. Everything in the universe gets dismantled down to isolated particles in a finite amount of time. The Big Rip gives you a hard deadline, a specific final moment. Depending on how fast the phantom energy grows, some models put that around 20 billion years from now. Others push it further out. Either way, everything ends at once, all at the same time, with nothing left. The Big Crunch runs the other direction. Dark energy weakens or reverses, or something we haven't measured yet causes gravity to take back over. The expansion slows, stops, reverses. Galaxies start falling back toward each other. The whole universe collapses inward. Temperatures climb, density climbs, and eventually everything compresses back into a singularity. It mirrors the Big Bang, but backwards. For a long time, the Big Crunch seemed like a low-probability scenario, mostly because every measurement we had suggested dark energy was pushing expansion faster and faster. But the 2024 DESI survey results changed the conversation. The data hints that dark energy may not be constant. It may be weakening over time. That's not confirmed. But it moved the Big Crunch from pure speculation to something physicists are taking seriously again, which connects directly to the Big Bounce. If the Big Crunch happens, what comes next? Loop quantum cosmology says the collapse doesn't end in a singularity. Quantum repulsive forces stop the compression before you hit infinite density, and the whole thing rebounds into a new expansion, a new universe. What we call the Big Bang may have been the bounce from a previous collapse. The Big Bounce doesn't technically end the universe, it restarts it. Whether that counts as dying depends on your definition. Now, vacuum decay. This is the one that bothers people the most, and for good reason. Quantum field theory says our universe might be sitting in what's called a metastable vacuum state, a false vacuum, stable enough to last billions of years but not the lowest possible energy state. Think of it like a ball sitting in a valley partway up a hill. It looks stable, it's been stable for 13.8 billion years, but it's not at the bottom, and quantum mechanics allows for tunneling. Somewhere in the universe, a quantum fluctuation could nucleate a bubble of true vacuum, a region where the laws of physics flip to their actual ground state. That bubble expands at the speed of light. You don't see it coming. There's no warning. It hits, and the laws of physics inside it are simply different. Different particle masses, different constants, different everything. Nothing that currently exists survives. The Higgs boson measurements suggest we might actually be in this metastable state. Most physicists think if vacuum decay were going to happen, it would have happened already, given the age of the universe. But nobody can rule it out, so you have 5 options. The slow fade of heat death, the violent shredding of the Big Rip, the collapse back into a singularity with the Big Crunch, the rebound into a new cycle with the Big Bounce, or the instantaneous rewrite of physics with vacuum decay. Which one is right depends entirely on understanding dark energy, and we're not there yet. In 1972, Jacob Bekenstein noticed something strange about black holes. Their entropy wasn't proportional to their volume but to their surface area. That's weird. Think about it. You pack more stuff into a box, the information content grows with the volume. That's how everything works. Black holes don't do that. The information scales with the surface wrapped around them, not the space inside. Bekenstein was a graduate student when he figured this out. Stephen Hawking confirmed it shortly after. And what most people miss is that this wasn't just a black hole quirk. It was a hint about the nature of reality itself. Gerard at Hooft took that hint seriously. Leonard Susskind took it further. What they proposed is called the holographic principle. The idea is that everything happening inside a region of space, every particle, every interaction, every bit of physical information, can be fully encoded on the boundary surface surrounding it. Like a 3D hologram stored on a flat piece of film, you're not losing information. You're just discovering that the volume isn't where the information actually lives. The surface is enough. The surface is everything. Most physicists heard this and didn't know what to do with it. It sounded more like philosophy than physics. Then one Maldacena showed up. In 1997, Maldacena published a paper that changed the field. He demonstrated that a theory of gravity inside a negatively curved space, called anti-de Sitter space, is mathematically identical to a quantum field theory living on its boundary, with no gravity at all. Two completely different theories, same physics. This is the ADS/CFT correspondence, holography made concrete, made mathematical, made useful. His paper has been cited tens of thousands of times. It's one of the most referenced papers in the history of theoretical physics, not because anti-de Sitter space describes our universe directly. It doesn't. We live in de Sitter space, which curves the other way. But the tools Maldacena built work. String theorists use them. Condensed matter physicists use them. People studying quantum information use them. The correspondence opened doors that nobody expected. Here's what most people miss about ADS/CFT. It isn't just a curiosity, it's a working dictionary. You have a problem in quantum gravity that's too hard to solve? Translate it into the boundary theory. Solve it there, translate back. Physicists have used this approach to study things like black hole thermodynamics, strongly coupled quantum systems, and the behavior of matter at extreme densities. The math works even when the intuition fails. That's what makes it powerful. It's not a proven theory of our universe, but it's a proven mathematical tool, and in physics that matters enormously. Now, the simulation hypothesis. This is where things get messier. Nick Bostrom laid it out in 2003. His argument runs like this. Either almost every civilization destroys itself before it can build the computing power to simulate conscious realities, or advanced civilizations exist but have no interest in running such simulations, or we're almost certainly inside one right now. One of those three has to be true. If you believe civilizations survive and would run simulations, the math says simulated minds vastly outnumber real ones. So statistically, you're probably not real. It's a clean logical structure. It's spread everywhere. Elon Musk said the odds were not in a simulation are 1,000,000,000 to 1. Physicists got asked about it constantly. Some took it seriously, some didn't. Here's the honest answer. The simulation hypothesis is not physics. It borrows the aesthetic of physics. It uses words like information and computational substrate, and it sounds rigorous. It isn't. There's no proposed mechanism you could test. There's no prediction it makes that differs from a universe that isn't simulated. If you can't distinguish it from the alternative, it's philosophy. That's fine. Philosophy matters. But it's not the same thing as what Maldacena did. What Maldacena did produced equations, produced predictions, produced tools other researchers could use. The simulation hypothesis produced interesting dinner conversations and a lot of YouTube videos. The confusion is understandable. The holographic principle genuinely does suggest that reality might be less three-dimensional than it looks. That space itself might be emergent, built from information encoded somewhere else. That's a strange idea, a destabilizing idea, and when people hear that, they reach for the nearest frame that makes it feel familiar. A simulation feels familiar, a video game you could understand. An encoded boundary surface in curved space-time is harder to hold on to. But the gap between those two things is enormous. One is a mathematically grounded framework actively solving real problems in physics. The other is a philosophical conjecture dressed in technical language. The holographic principle is serious physics. The simulation hypothesis is what happens when serious physics leaks into philosophy and the internet finds it. The universe appears to be almost absurdly well set up for the existence of complexity. Not a little well set up. Absurdly. The numbers are almost offensive when you look at them closely. Gravity, electromagnetism, the strong nuclear force, the mass of an electron. Each one sits at a value that makes atoms, stars, and eventually you possible. Nudge any of them slightly and nothing works. Gravity a bit stronger and the universe collapses in seconds. A bit weaker and matter never clumps. No stars, no planets, nothing. The cosmological constant is the worst example. It controls the energy density of empty space. Its measured value is so close to zero that physicists calculate it's fine-tuned to roughly 1 part in 10 to the power of 120. That's not a typo. 120 zeros. Nothing else in all of physics is that precise. If it were slightly larger, the universe would have expanded too fast for gravity to ever pull matter together. No galaxies form, no stars ignite. You get an enormous cold void and that's it. Physicists find this number deeply uncomfortable. Most of them won't say it out loud, but they do. Here's what most people miss about fine-tuning. It's not a fringe concern. It's not something crackpots invented. It's sitting right in the middle of mainstream physics, and nobody has a clean answer for it. You can't just hand-wave it away. The constants are what they are, and the question of why they're that and not something else is genuinely unanswered. There are 3 serious responses. First, the anthropic principle. The idea is almost embarrassingly simple once you hear it. You can only observe a universe that permits your existence. We're here asking the question, so of course the universe we find ourselves in supports life. A universe with the wrong constants has no observers wondering about constants. The sample is biased by definition. This is the weak anthropic principle. Most physicists accept it as technically true. It doesn't feel satisfying, but it's hard to argue with the logic. The strong anthropic principle goes further. It claims the universe's constants aren't just compatible with observers. They must produce observers. The universe requires intelligent life in some fundamental sense. That's where most physicists get off the train. It's speculative. It borders on unfalsifiable. Saying the universe must produce us is a very different claim from saying we only see universes that can produce us. One is selection bias. The other is something closer to purpose. Physics doesn't have tools to test purpose. Second response, the multiverse. If inflation runs forever and produces infinite bubble universes with randomly varying constants, then somewhere in that distribution are universes with constants that work. Observers will always find themselves in the ones that work. Fine-tuning disappears because it was never tuning at all. It was just selection from a large enough sample. This is genuinely elegant. It's also the reason some physicists care so much about the multiverse. It's not just philosophical novelty. It's a potential solution to a real problem. The issue is you can't test it. Other bubble universes are causally disconnected from ours by definition. You can't confirm the lottery was fair by inspecting only the winning ticket. Third response, design. Some thinkers, not all of them physicists, look at the numbers and conclude intentionality. The precision looks like deliberate engineering. This argument has existed for centuries in various forms. It sits outside the scope of physics. Science tests mechanisms, not intentions. Whether fine-tuning points toward a designer is a philosophical or theological question, and dragging it into physics doesn't make it more answerable. Most physicists leave it there. What makes the fine-tuning problem different from most open questions in physics is where it lives. Dark matter is an open question. We expect to solve it with better detectors. The CMB has gaps. We expect better telescopes to fill them. Fine-tuning sits at a different boundary. It might be a question physics can answer with a full theory of the multiverse, or it might be the kind of question that science reaches and then stops, not because we failed, because it requires tools we don't have and may never have. That bothers physicists in a specific way. It's not the same discomfort as not knowing the answer. It's the discomfort of not knowing whether an answer is even possible. The universe giving us exactly the constants needed to ask why it gave us exactly these constants is either the deepest clue we have about the structure of reality or a profound coincidence, and physics has not yet found a way to tell the difference.